அப்படியே ஸ்டார்ட் பண்ணுங்க.
சரி, ஓகே.
ஒரு 2 மினிட்ஸ் விட்டுடுங்க, நான் மியூட் பண்ணிக்கிறேன். நீங்க 1 மினிட் விட்டுருங்க, அப்படியே கொஞ்சம் ஸ்டார்ட்.
ஓகே,
ஸ்டார்ட் பண்ணிடுங்க.
Greetings, students. We'll see about machine instructions and addressing modes today. So in general, in microprocessor, for what the instructions are used and what is addressing modes, we'll see one by one. And the problems which regarding these machine instructions and addressing modes, we'll see in this class, right? So the processors are instructed by using this machine instructions. So what has to be done? What is the operation which has to be done by the processor? We are just giving the commands by using this instruction sets, right? The different ways in which we can access the processor or the memory. That is what addressing modes is. So how we are going to give the data? What is the different ways we are going to give the data, right? So we classify that as addressing modes. So what are different types of instruction sets we have? So we can say that we can access the processor by using 3-byte instructions or 2-byte instructions, 1-byte or 0-byte instructions, right? So binary codes which are used to specify the operations which can be performed by the microcomputer is called as instructions, right? In instructions, we'll be having the opcode, operand. Right, opcode says what has to be given. So what is the operation which has to be performed, whether it is going to do addition operation or multiplication, subtraction, division, or logical shift, rotate. So what are the things that we call this as the mnemonics, all right? And then operand 1 and 2, that says for addition we are going to add 2 numbers, so that those numbers will be given in the operands, right? The general sequence of instruction flow is fetching, decoding, and executing. When an instruction is given, the processor will fetch the instruction and then it will decode and see what has to be performed, and then it will execute the instruction. So while executing, it can get the data directly or it can be from the memory. So from the memory, the data will be accessed and then it will be executed and the resultant will be stored in the memory. Right, different types of instruction formats are, as if I said, we have 3 address instructions, 2 address instructions, 1 address, and 0 address instruction format. So in 3 address, so the resultant address is one of the location. In the other two locations, we'll be having the operands. So operand 1 and 2. And then one location is to see the operand which has to be performed. What is the opcode which has to be given to do this addition operation? So that carries one location. So on the whole, this 3-byte instruction this is a 10-byte instruction. So this is a 3 address location instruction. It occupies 10 bytes in the memory location. Right. So here 4 words for each instruction fetch, 2 words for operand fetch, and 1 word for the result to be packed in the memory. So this is what a 10-byte instruction format is. So this is 3 address instruction format. Next is 2 address instruction format. So here you will be having the opcode which has to be done. So what has to be done? Whether it is addition or subtraction, whatever it is. Followed by resultant, where the result has to be stored and where is the operand present. Right? So we call this as the 2 address instruction format. So you'll be having 2 address locations. One to store the result, other one is to get the operand. Next is 1 address instruction format. So here default address, by default the address, the operand 1 will be given in this instruction, then the operand 2 will be in the accumulator. So with these two are added, the accumulator content and the operand 1 which is given here is added and the result will be stored in the accumulator. So we say this is a 1 address instruction format. So next is 0 address. That is, in this way, this comes under the implied addressing mode. So none of the operand is present in the instruction. If that is the case, we say this as zero address instruction format. So here directly it will access the content from the stack location. Then different classifications of instruction sets. So we will be having data transfer instructions, logical instructions, arithmetic instructions, shift and rotate instructions, process control instructions, branching instructions. So these are general classifications of instructions we have. Data transfer instructions, the content is moved from one location to other location. It can be either between registers or from memory to register or register to memory, or from memory to the input device, or from the output from the um, memory input device to the memory, or from the memory to the output device. So this is the sequence flow. So the examples for this data transfer instructions are, we can say load, store, move, exchange, input, output, push and pop instructions. These push and pop instructions will be used during interrupt, right? So before executing an interrupt, we will be moving the content of the current program counter value or on the IP address value or code segment value to the stack. So for that, we'll be using this push. And while coming back from the subroutine or subprogram after execution of the interrupt, we'll be using this pop instruction to retrieve the data which is stored in the stack location. This is what data transfer instructions are. So next is data manipulation instructions. Right? So some operation will be performed by these data manipulation instructions. So what are those? It can be arithmetic operation, logical operation, shift operation, or rotate operation in that way. Right? Few arithmetic instructions are increment, decrement, addition, that is add, subtract, multiply, divide, addition with carry, subtraction with borrow. Negative is used during subtraction, that is to take the 2's complement of a given number. So by using this negative instruction, it will directly give you the 2's complement result. Then few logical and bit manipulation instructions are, so for clear, we will be using CLR. For complement, you will be using COM. For AND, AND, or. So this mnemonics will be varied for each and every type of the processors. So each and every processor will have a set of mnemonics which can be used to instruct the processor to do a specific task, right? So these instructions, these mnemonics will be provided by the manufacturer for each and every processor. So by using those data sheets, we can write program and we can instruct the processor to do a specific task. So for clear, the clariflag, we are using CLRC. So this instruction is not common for all the processors. It varies from register to register, so from processor to processor. Set the carry flag, then complement the carry flag, enable the interrupt, disable the interrupt, XOR operation. So these are the few logical and bit manipulation instructions we have. Next is logical left and right shift, then rotate left and rotate right. So for this, you'll be using SHR for right logical shift, SHL for left logical shift, RYR for rotate right, RYL for rotate left. Similarly, we can also have similar type of instructions for logical left shift with carry, right shift with carry, rotate left through carry, rotate right through carry. So for this also we'll be having few sets of instructions. So next is program control instructions. So all the branching instructions, jump, skip, call, return, compare, test. So these are the few examples of program control instructions, right? And its corresponding mnemonics are given here. So we are going to see an example problem which is asked in the previous year gate question papers. So consider the following program segment. Here we are having three registers R1 and R2, R3. These are general purpose registers. Program is given. So what is asked is, what is given is, assume the content of the memory location to be 3000. So that is move R1, 3000. This is the first line of the program given. That means 3000 is the address location. From the content in that location is moved to the register R1. So what is given in the question? Assume the current of the memory location 3000 is 10. So 10 is the value which is passed to the register R1. Right? And the content of the register R3 is 2000. So in R3 we are having the content as 3000. The content of each of the memory location from address location 2000 to 2010 is 100. The program is loaded from the memory location 1000. All the numbers are in decimal. This is what given as the question. So the numbers given in this program are decimal. The count is 3000 is 10. So 10 is the value which is moved to the register R1. So next what operation has to be performed? From the 2000 location, the content in 2000 location is moved to the register R2. So in 2000 location, what's the value we are having? We are having 10. Sorry, 100. 100 is the value which is there from the address location 2000 to 2010. Right? So 100 is moved to the register R2. After that, we are going to add register R1 and R2 content. Right? So 100 is added with R1 content. R1 content is 10. So when we add 100 plus 10, we'll be having 110. That is the resultant value which is stored in the register R2. Right? Next, the R2 content is moved to the register R3. Right? So in R3, we'll be having 110. Then increment the value of R3 by 1. Right? So R3 value will be 111. Then decrement the R1. This is the count. So we are given 10, no? So decrement it by 1. So now the count becomes 9. Check whether the value of R1 is 0 or not. If it is not 0, jump to the location loop, repeat the process till it is made 0, and then stop the program. This is a sequence of sequence flow of this program, right? So what is asked is, right? We are asked to assume memory is byte addressable and the word size is 32 bits. If an interrupt occurs during the execution of an instruction, increment R3. So what is the return address which will be pushed onto the stack? So while executing the sequence flow of instruction, right, when an interrupt occurs while executing the increment R3 instruction, so what is the address which has to be passed to the stack so that while returning back, we can start executing from the next line of the instruction. So if the interrupt occurs now, the control will be transferred to the subprogram. So to come back, we need the address location where we stopped executing. Right? So while executing this interrupt, what is the address which has to be pushed to the stack? This is what the question is. Right? Always keep it in mind. Alright? While executing an instruction, if the interrupt occurs now, that current instruction will be executed. And then only we'll stop executing the main program and we'll go to the subprogram. Right? What is given here? Memory is byte addressable and the word size is 32 bits. Right? The word size is 32 bits. So here, for each and every instruction, the number of words which is required is given. So one word size is 32. So here, for the first instruction, move R1, 3000, the word size is 2. So 32 into 2 is 64. To store the 64 bits, how many byte location is required? We have to calculate. So for 32 bits, we require 4 locations. 8-bit or location, right? For 8 bits, we require 1 location. For 16 bits, 2 location. Next 24 3 location. 32 we need 4 locations. So this instruction is the number of words required for this is 2 words. So it requires 64 bits. Then it requires 8 locations. So the starting address of the program is given as 1000. This is what given here. Here starting address is 1000. The first line of the instruction requires 8 locations from 1000 to 1007. The other consecutive instructions occupies or requires 1 word. Right, 1 word is 30 bits. Then that means 4 locations are required to store this opcode for this instruction move R2, R1. Right, from 1008, 9, 10, 11. So 4 locations are required. Similarly, for the next instruction, we require 4 locations, then 12 to 14. For next instruction, it requires 16 to 19. Then for next instruction, it requires increment R3 also requires 4 locations. So 1020 to 1023. So in the question it is given interrupt occurs during execution of increment R3 instruction. Right, during that instruction if the interrupt occurs, that particular instruction will be executed and then the control will be transferred from the main program to the subprogram. So while coming back, I had to start executing from the decrement R1 instruction. So the starting address is 1024. Then this is the address which has to be 1024 is the address which has to be pushed to the stack. Right? So therefore, here the correct answer is answer option C. That is 1024. So this is the value which has to be pushed to the stack to come back to the next line of the program while executing. This is how we are supposed to find, right? So next is in the same program, what is the other question which is asked is, right, the program remains the same, right? All other conditions remains the same. So what is asked is the number of memory references for accessing the data in executing the program completely is. So how many number of memory references accessing data? Number of memory references. So how many memory references are required for this execution of the program? So how many memory accessing is done while executing this program? That is the question which is asked. So you can calculate it by using first finding the number of memory accessing inside the loop. So we know the loop count is 10. So how many memory instructions are there inside the loop? Move R2, R3. Move R3, R2. So two memory instructions are there, right? So two memory references are there. So since the loop count is 10, 10 into 2 is 20. So we'll be having 20 memory references inside the loop. And outside the loop, we have one memory reference, that is move R1, 3000. So I can simply say, right, we require 21 memory references. That's what the option is. Answer D, 21. So how it is obtained, you can see here now. So two memory references inside the loop. Right, so 2 into 10, the loop count will give you 20. Plus outside the loop, we have one memory reference. So on the whole, we can say 21 memory references are required. So consider one more case. So here how to calculate the physical address. Right? Code segment addresses, if the code segment value is 348AH and the instruction pointer value is 4214H, then the 20-bit physical address from which the code is accessed will be. So the physical address has to be calculated. We know in general to calculate the physical address, the formula is segment address into 10. This is the base address of the code segment register. That into 10 plus effective address or offset address. So here the effective address is stored in instruction pointer IP. Alright, so code segment value is 3480A. 3480A into 10 plus 4214 gives you 38AB4H. So when we add this in hexadecimal format, we'll be getting this as the result. So the answer option is D. That's the right answer. Right? This is in this type we can expect a equation. Right? But it will not be directly given. Some twisting will be done. So next one is consider the case. Before the execution of pop instruction, the stack pointer points to FFFFH. The content of the stack pointer after execution of pop instruction will be. So this is what the question which is given is. So first recall what will be done during push and pop instructions. So we know during push instructions the stack pointer content will be decremented by a value of 2 for 8086 microprocessor. Right? Since it is a 16-bit processor, the content of stack will be decremented by a value of 2. Right? For pop instruction, the content of stack pointer will be incremented by a value of 2. For a 16-bit processor, if that is the case. So here if we consider a 16-bit processor, all right, for pop instruction, the stack pointer value should be incremented by a value of 2. So incrementation of F leads to 0, 0, 0, 0. Then addition of one more with it gives you 0, 0, 0, 1. So that is the right answer, answer C. So you can check it out. So this is the right answer, C. So after the execution of the pop instruction, the stack pointer is automatically incremented by 2 to point to the next word on the stack. Right? So this is what the address will be, which will be stored in the stack. So next question is, for computer based on 3 address instruction formats, each address field can be used to specify which of the following. So for a computer based on 3 address instruction format, if 3 address instruction format is given, each address field can be used to specify which of the following. This is what asked. So the options are S1, a memory operand, S2, a processor register, S3, an implied accumulator register. So here the options given are either S1 or S2, S2 or S3, only S2 and S3, all of S1, S2 and S3. So each address field can be used to specify. We can use the address field to specify either S1 or S2. That is, it can be either a memory operand or a processor register. So we can say an implied accumulator register. So to access the accumulator, we will not be requiring an operand. We can directly do it. So without operand, we can just do. So that is not the right answer. So the right answer is we can use memory or processor register. So what is RISC and CISC process? Complex instruction set computer. Next one is RISC, reduced instruction set computer. Right? What in complex instruction set computers, right, we'll be having a large number of instructions which is classified as complex instruction sets. Alright, CISC process will be having typically 100 to 250 instructions. The CISC process that we provides direct manipulation of the operands residing in memory. So we can directly access the content from the memory. But here for the CISC process, we require more instructions and addressing modes. And more hardware logic is needed to implement and support them. Right, so this is what CISC processor is. Next is RISC, reduced instruction set computer. So RISC architecture is used to reduce the execution time. So this is the main advantage. So this is used to reduce the instruction time, execution time of the instructions. So here relatively few instructions will be there when compared to the complex CISC processors. And then you'll be having few instructions and few addressing modes. So here, since we are having few addressing modes and instructions, most of the operations will be done with the registers of the CPU itself. Right? In 2013, a question is asked in this way. For 8085 microprocessor, the following program is executed. So while executing this program, So what will be the accumulated content at the end of the program? So this is what a question which is asked in 2013 GATE question paper. So move immediately A comma 05, move immediately B comma 05, add B, decrement B, increment pointer, so jump if it is not 0. So check whether the value of B register is 0. If it is not, jump to the pointer location, repeat the process, then add immediately the value 03 with the content of the accumulator. So this is what the program is given. So after the end of the execution of the execution of the program, what is the resultant stored in the accumulator? This is what the question is given us. Right. First step is accumulator content is moved with the value of 05. So B register will be having a value 05. So this is immediate addressing mode. So move immediately A comma 5. So B value is 5. Add the A with B. So you'll be having 5 plus 5 is 10. Alright. So after the value is added, the resultant will be stored in the accumulator. So the value which is stored in the accumulator is 10. Equivalent of 10 in hexadecimal is A. So that's the value which will be there in the accumulator. So then decrement B. So B gives the count. So we are going to decrement the value of B by 1. So that is 5 becomes 4 now. I check whether it is 0 or not. If it is not 0, jump to the address location specified. So pointer PTR. So jump to that location. Again add the content of B with the accumulator. So what's the current value of the accumulator? The current value is 10. So 10 plus 4 gives you 14. Right? Equivalent of 14 hexadecimal is E. So E is the value which will be there in the accumulator now. Then again decrement the value of B. Check whether if it is 0 or not. Repeat the process. Then again add the content of B register with accumulator content. So now the B register value will be, after decrement it is 3. So 3 will be added with the resultant value E, that is equal to 14. 14 plus 3 gives you 17. Equivalent of 17 is 11H in hexadecimal. Now decrement the value of B, that becomes value 2. Now again repeat the process. So after repeating, you will be getting the resultant value as 14H. Now decrement the value of B. So B becomes 0. If it is 0, come out from the loop. So now what has to be done? Add 03 with the accumulator content. So the resultant is 14H. So add 3 with it. So you'll be getting 17H. So that will be the immediate value. That will be the resultant value after execution of the program. So the option is answer A, which is 17H. So next is rotate left and the MSB value content will be moved to the carry location. So rotate left. This is rotate left, logical left. Next is rotate left through carry. So RLC is rotate left, RAL is rotate left through carry. So you can see the diagram here. It is clearly given. So MSB becomes LSB for rotate left. MSB becomes the carry flag content. Carry flag content becomes the LSB for the rotate left through carry. So instruction is RAL. Instruction format is RAL. There is a question in 8085 microprocessor. The content of the accumulator and the carry flag are A7 in hexadecimal and 0 respectively. So hexadecimal value of accumulator is A7. So A7 is A is 10, equivalent is 1010. For 7, the equivalent is 0, 111. Right, so what is the question which is given is, this is the case if A7 is the content of the accumulator and 0 is the content of the carry flag. Under this condition, if the instruction RLC is executed, so rotate left, not with through carry, it is without carry, right? RLC is executed. Then the content of the accumulator and the carry flag respectively will be. So rotate left now, from right to left will be moving. So MSB becomes LSB. Also MSB will be moved to the carry flag. So this is what RLC is. So you can check it out here. 1010 Just one left shift is done. Then this one becomes the LSB. This 0 becomes the MSB. And this 0 becomes the fifth bit position. This 3 becomes third bit position, and this will be first. Then MSB will be loaded in the LSD part. So that one is loaded here. Also, the same value of 1 will be loaded into the carry. So I can say, so here the equivalent is 0100 is 4. Then all 4 ones is F. So 4F will be the current content and the carry will be 1. So the option is D. So D is the right answer. So this is logical left without carry. Next is execution time calculation. So you can check it out here for 8085 microprocessor whose operating frequency or working frequency is 30 megahertz. The clock period is 3 megahertz. So this is the clock frequency given 3 megahertz. Then the clock period is 1 by 3 of the microsecond. So we know no T is equal to 1 by F. Right? Similarly, T is equal to 1 by 3 into 10 power 6. F value is 3 megahertz. So 1 by 3 into 10 power 6. So that gives you the value of 0.333 microseconds. If you take no operation, right? No operation requires 4 T states to execute it. Right? Each and every T states we will say it as 1 clock period. Right? If it is 4 now, the clock period value into 4. So 0.333 microsecond into 4 gives you 1.33 microsecond. So that is the time which is required to execute the instruction no operation. So next is the same program with a different clock frequency is given. So this is also a previously asked gate question. Right? If the clock frequency is 5 megahertz, alright. If the time required to execute an instruction is 1.4 microsecond, then the number of T states needed for executing the instruction is. So what's the number of T states required? So T clock, we know clock frequency is given. The time of this clock signal will be T clock, that is T is equal to 1 by F. So F value is 5 megahertz. So substitute the value of 5 megahertz here and you will be getting the T clock period as 0.2 microseconds. So this is the time which is required to execute. This is the time required for a single clock signal, single clock pulse. Right? So number of T states is 4. Sorry. We are supposed to find the number of T states. So that is equal to, here what is the thing we have obtained? The time required, the maximum time required is given as 1.5 microseconds. So 1.4 microseconds by single clock signal period. So that is 0.2 microseconds will gives you the value of 7. So 7 is the number of T states required here. So the option is answer C. Excuse me. So here there is one more question which is asked in GATE 2011 question paper. An 8085 assembly language program is given below. Assume that the carry flag is initially unset. That means it is clear. It is not set. The content of the accumulator after the execution of the program is. This is what they have asked you by giving the following sets of instruction. Move immediately A, 7. That means A is the value which has to be loaded to the 7 is the value which has to be loaded to the accumulator A. Then RLC, rotate left through carry. Next is move B, A. Then RLC, then add B, next RRC. RRC is rotate right. So we can check the answers now. So A value is 07. So 07, the equivalent is 0000. For 7, it is 0111. For carry flag, it is 0. For accumulator, for RLC, that is rotate left. So for accumulator, the value is, the present value is 0111. So after one logical left shift, it becomes 0000, then 111 followed by 0. The MSB becomes the LSB here. So the equivalent now is 0E. That is the content which is moved to the B register. Next is rotate left through carry. Again, repeat the process twice. So again, 2 times logical left shift will give you the value here. The equivalent of the final case for the second case is 38. So 38. So next is add B. So the B register value is now 38. So add the current of A. So A register value is now 'So in B we are having 0E. So add 38 with 0E, that the value will be 46. So 46 is the value which will be stored in the accumulator now after execution of add B instruction. Again rotate right through carry. So that leads to the value. Just give one logical right shift. So you'll be getting the value as 0010 followed by 0011. Right, so the equivalent is now 23, so 23, and the carry flag content will be 0. Initially it is 0. Again now the last value LSB value will be moved to the carry flag. The LSB value is 0, so 0 will be passed to the carry. So now the carry flag content is 0, and then the content in the accumulator is 23. So 23. The option is C is the answer, right answer. Which method bypasses the CPU for certain types of data transfer? Say the answer is to bypass CPU and access the memory directly, we go for direct memory access. This we know now, it was studied in CA. Then different addressing modes. So we have seen the few examples and a few problems related to machine instructions now. Next we'll be seeing the problems related to addressing modes. As today's topic is machine instruction and addressing modes. So we already know the various methods used to access the instruction operands is called as the addressing modes. So first field is the opcode field, then followed by the operand fields. The operand can be in register or memory, or it can be from IO ports. So 3 basic addressing modes are immediate, register, and memory addressing modes. These are different classifications of addressing modes. 586 microprocessor. First is implied, that is no operand present. Register now moving the content between registers. Immediate na data is part of the instruction. Direct na, right? So the content where the operand is the operand location is directly specified in the instruction itself. It's address only part of the instruction. Register indirect means here where the content is, so that will be stored in a register. That is, in register will be having address location. From that address location, the content will be moved to the specified location in the program. So indirect addressing. So directly we will not be saying where the content is. That location is stored in the register. So that is indirect addressing mode. Next is indexed. When we go for source index or destination index, we say it as indexed addressing mode. Then register relative. So some relative value will be added with the base, or that is BP or BX, or SI or DI. So we say it as register relative addressing mode. Then base plus index. So to calculate the physical address, we'll be taking the effective address plus data segment into 10 value. Our segment is 10 to 10. So here base index na effective address location is base plus index location. Relative base index na will be having base address, index address plus some displacement value. So this gives the effective address. This effective address will be added with the segment address into 10 value to obtain the physical address. So the content in that location will be used in the instruction. So that is what relative base index is. Next is string. Next is IO port addressing mode. Next is program memory addressing mode. So we have direct type, relative type, or indirect type. So there also we have intersegment or intra-segment. So it has been classified as intersegment. Intersegment means moving from one segment to other segment. Intra-segment means moving within the segments. So the branch instructions or loop instructions will be moved within the segment. Now we say it as intra-segment instructions. If it is moving to the other segment, now we say it as inter-segment jump or inter-segment call instructions, whatever it is. So there we can we can access it directly or indirectly. So what I said now, that is given here, implied addressing mode. Now there is no operand present. Immediate na address is part of the content is part of the instruction. So direct na directly given. Right, register na between registers. Direct, indirect, relative, index, everything I said you. Examples for this is given. Move BL, 26. This is an example for immediate addressing mode. Implicit or implied is no operand is present. Set the carry flag or clear the carry flag. CTC you can say. So move CL, in brackets 9823 na. Then this is an example for direct addressing. Move BX, CX is register addressing. If CX is put in the bracket na, then that is register indirect addressing. That is move DI, DI in brackets, BX. That means BX content is moved to the location specified in the DI register. Next is placed index. That means base and index register together gives an effective address, which has to be added with the segment address. The content in that location, the resultant location is moved to the AX register. This is what base index. Then relative na displacement will be there. Relative base index na base value index source or destination index value plus relative address or displacement value will be there. Example for direct program memory is jump to the location specified in the instruction. Jump 2000 na go there to the location 2000. This is direct type. Relative na from the current location either move twice, 2 locations or 3 locations in that way. Relative address is given. That is from the current location. Indirect means we can move either to the same segment or to the other segment. If it is same segment, now we say it as intra-segment jump. To the other segment, now we say it as inter-segment jump. So now consider a processor with 64 registers and an instruction set of size 12. Each instruction has 5 distinct fields, namely opcode. So one field is opcode, other one is 2 source register identifiers, 1 destination register identifier, and a 12-bit immediate value. So this is what given. Each instruction must be stored in memory in a byte aligned fashion. If a program has 100 instructions, the amount of memory in bytes consumed by the program text is. This is what the question given is. So first we have to find. So it says each instruction has 5 distinct fields. Right? Number of bits for each and every field is given and given. Right? So on the whole it is, we are supposed to find 2 source register identifiers. So each register occupies 6 bits, right? 2 source register na 6 plus 6. 1 destination register, again it is of 6 bits. Alright. Then 12 immediate bit. 12 bit is immediate bit. Right? And the opcode bit is 4. So on the whole, one instruction size is 34 bits. So we are obtaining this from the question given. They are going to consider a processor with 64 registers. And the instruction set of size 12. Instruction set is of size 12. Right? So here each and every instruction occupies 34 bits. Then one instruction occupies 5 byte locations. 5 bytes or 5 locations. Right? Then if it is, that is for one instruction, 100 instructions will occupy 500 bytes. 5 byte into 100 will give you 500 bytes. So calculate it for one instruction and then calculate it for 100 instructions as if it is done here. For execution of single instruction requires 34 bits. So 34 into 100. So 34 now it needs 5 locations. So in one location you can store 8 bits now. So 34 bits now by default we require 5 locations. That is, it requires 5 byte memory location. So 5 byte into 100 gives you 500 byte locations. We consider the same program which we used before. The same program, first we have found what is the segment, what is the stack location content after the execution of the interrupt while executing the interrupt instruction, while executing the instruction increment R3. Right, we got the value. The other cases, how many memory accessing is there in this program? That's the second question which is asked. So the third question is, assume the memory is word addressable. After the execution of this program, the content of the memory location 2010 is. So this is what the next question which is given. So what's the content of the memory location 2010? After execution of this program. Right, this is what the question which is given. So the explanation is given here. So we know R1 count is 10. So the loop count is 10. So what has to be done here? R3 value is 100. That is, in the 2000 location, we are having the value 100. So move that 100 to the register R2. So add 10 with it. That is the R1 value with it. You will be getting 110. So 110 is moved to register R3. So the current value of the R3 is 110. Then increment it by value of 1. Then decrement the R1 content. The loop count is getting decremented. Alright. So what is asked is, after execution of the whole program, what will be the content of the memory location 2010? So the explanation is given here. So when R1 value is 10, and the memory location which we are accessing is 200. So 2000. The content in 2000 is 100. 100 plus 10 gives you 110. So this is what given here. So here you are having, in 2000 location you are having 100. 100 plus 10 gives you 110. So that is when R1 value is 10. All right. So then there is a loop, no? After getting out from the loop only will be, then increment the value of R3 by 1. R3 value will be incremented by 1. So the resultant here is R3 content is so here the R2 content is R3 plus R2, that is 110, right? So R2 plus R1 is 110. Then move that value to the R3 location. Increment R3. Right, the R3 value is now 111. Then decrement R1. So the loop count is given. So if the value of register R1 is 9, then the 2001 location will be 10109, since there is a decrement here. Decrement R1 by a value of 1. So R1 value will be 10 minus 1 is 9. Alright. So 9 will be added with 2000 location value. So that is 100. You will be getting 109. Then decrement the value of R1, that becomes 8. So 8 is added with 100. Now you will be getting 108. So repeat the process. 7 plus 100, 107, 6 plus 100, 106, 5 plus 100, 105. So this process will be repeated till R1 value is 0. So if R1 value is 1, you will be having 101. If R1 value is 0, the loop breaks. So the memory value will be 2010, that is equal to 100. That's what given the question, no? From 2010 to 2010, that is 2000 to 2010, the value will be 100. So at location 2010, the value is 100. All right. So even if you are repeating this process here, at one point, what is the resultant you are having? You are having the same value 100. So because B1 value is decremented from 10 to 9, sorry, from 10 to 0. So after adding that with the accumulator, the accumulator content will be 110, 9, 8, 7 in that way till it is 101. So last value is 10 is 2010. That is the last location. There will be having the value of 100. So this is what the right answer is, 100, which is option A. Next, we see few more problems. Anti-dependency, and then time delay calculation we can see. Right, we know, no? Find the machine cycle of for 8051 if crystal oscillator frequency is 11.0592 megahertz. So we know crystal oscillator frequency is given in the equation. To calculate the machine cycle is number of cycles per frequency. The time is 1 by f. Right, time in nanosecond is 1 by 11. That is the crystal frequency. Right, you can substitute there. So that gives you the time. Right, so the time paid for this 11 megahertz is 90.42 nanoseconds. Right, to calculate the machine cycle period, the formula is machine cycle period is 1/12 of the crystal frequency. So it is 1/12 of the crystal frequency. So now we converted the frequency into time. All right. So 12 into the value which is taken for the time calculation. So that gives you 1.085 microsecond. So this is what the time which is required for a execution of single mission cycle. So next is types of interrupts. So we have maskable interrupt, non-maskable interrupts. We know now maskable now it can be enabled or disabled. Non-maskable interrupt now we cannot enable or disable the interrupts. Next is on the basis of devices, we can classify the interrupt as external interrupt, internal interrupt, software interrupt. Right? Number of basic calls, basic cells in the 16 cross 4 RAM are. Now, how many number of cells are there in the 16 cross 4 RAM? So it consists of 16 words. Each is of 4-bit wide. So 16 into 4 gives you 64 binary cells. So here we will be seeing about the data path. So what are the terms which is present and how it has been done. Now we are going to access instruction path. There are few examples of few problems which is asked in that one by one. Right? So your next one is data path. At A data path. The CPU can be divided into data section and control section. Data section is called as a data path. Control section we call it as the control unit. So the terms which is present, what is bus, what is data bus, address bus, and how many bit each address bus, data bus, and control buses. So these all things we know. These are the basics which has to be known. Bus na collection of wires, we say data buses, number of lines which is used to transmit the data. Address buses, number of lines which is it is used to access the address locations. Right, control bus for transferring the control instructions will be using that program counter that is used to store the address of next instruction to be executed. Next is instruction register, instruction catch, arithmetic logic unit, data catch, then multiplexer, single cycle data path. So these are the cases we have. So about this and the problems related to this we'll be seeing in the next class, right? These things we'll be seeing in the next class. And its options, the answers, correct answers, it's wrong answers. So everything, these things we'll see in the next class. So with this, I'll be stopping with this time delay calculation. This number of, what is the mission cycle period? With this, we'll be stopping.